Hello, everyone. Welcome to Energy Trust of Oregon's Saving Energy video series. My name is Angelica Bomey. I'm an energy management coach working with Energy Trust of Oregon's industrial customers. Our presenter today is none other than Kevin Campbell. Kevin is an energy engineer and a program manager with us who supports the industrial organizations throughout Energy Trust's territory. With that, I'm going to kick it over to Kevin to get us going. Kevin?
Thanks, Angelica. So this video lays a foundation so we can begin to explore how your facilities use energy. We can then use that information to help estimate how much energy different pieces of equipment use and ultimately help inform identifying and prioritizing potential energy saving projects. The section is split into two parts based on the primary energy sources of most industrial facilities, that is electricity and natural gas. And let's start with electricity, and we'll begin with something that'll be familiar to many of you, an electric bill. So starting at a high level, you're all probably very familiar with the information in the upper right-hand corner, right? The current charge and the due date, but there's way more going on this bill than just those two things. So if we look a little bit lower down in the bill, you'll see the first high dollar items. These are the system usage charge, the off-peak usage, and the on-peak usage. And what I want to point out is each one of these has this kWh in the line item description. That stands for kilowatt hours, and those are the units of electric energy use in buildings and industrial facilities. The other thing I want to point out here is look at the amount for each one of these line items. So the total cost associated with just the energy use portion of this bill is, by and large, the majority of the bill cost. It's over $25,000. It's the biggest line items on this bill. Now, if we scroll down from there, we'll see there are a couple of other line items. These are the demand charge, the transmission charge, and the distribution facility capacity charge. These all have kW in the line item description. Now that's short for kilowatts, and kilowatts is a measure of your facility's demand or your peak demand. That's not the energy use. That tells us how much power your facility is pulling at any given time. And it's really a measure of the highest amount of power you're pulling off the grid over the course of a month. Now, what I do want to point out is that the line items here, the dollar amounts, they're notable, but they're not quite as high as the energy use part. And that's going to be the case for most industrial facilities throughout the state of Oregon. It is going to depend, though, a little bit on your billing schedule, your rate schedule, and then just how your facility uses energy and its power requirements. The other thing I want to call out here is most Energy Trust programs are specifically targeted at reducing the energy use portion of your bill, that biggest portion of most customers' bills. However, oftentimes when you do a project that saves energy, it might also reduce demand, so you kind of can get a double benefit with some projects. Now, if you find that maybe you really want to focus on reducing your demand at your facility, there are other programs that you can consider. They're called demand response programs, and your local utility might offer one of those. I encourage you to check in with either your local utility's key account manager or your Energy Trust representative to learn more about those programs and figure out how you can further manage your energy costs by participating in a demand response program. All right, so with that, we've got a little bit of an understanding of your electric bill. What I want to dig into next is that difference between power and energy. So power, which is often referred to as demand in the context of electric power systems, is a rate. So here it's shown as the rate of water leaving the spigot. For the spigot example, we may think in terms of gallons per minute or GPM. However, for electric power systems, we use units of kW or kilowatts. And because it's a rate, we think of it at any single instance of time. For example, you could say there's 2 gallons per minute of water leaving the spigot at this very moment. For the case of your facility, you might say, at this very moment, my facility is pulling 5,000 kW from the electric grid. Now, energy is a bit different. Energy is actually a quantity. Because it's a quantity, we want to think of it over some period of time. So for the water example shown here, it could be how many buckets of water were filled up over a 1-hour period of time. For the electric energy example, the quantity is kWh, which is short for kilowatt hours. And we often think of it in terms of energy use per day, or what was the energy use of your facility per month on your bill, or what was the energy use of your facility over the course of the year, what's its annual energy use. Now, what's really cool is your electric meter actually measures both the power, the kW side, and the energy, the kWh side. And again, if you want to manage your energy costs at your facility, your electric costs, you could say, you want to be thinking not only about the energy side, but also about the demand side. You can kind of manage both individually to get the biggest bang for your buck when it comes to energy management. So how you actually build for demand is a little more complicated. So let's take a closer look at that and an example of the peak demand for a sample facility. So what we're looking at here on the vertical axis, we have this facility's 15-minute demand measured in kW. Now this is a little unusual because it's called the 15-minute demand, but before I said demand or power was a rate, so it's at this very moment. What your utility is going to do though is they're going to take your demand for the facility and they're going to look at this 15-minute running average window, and that's when you're going to get billed on. So you actually don't get billed on these momentary spikes in demand. That gets kind of washed out over a 15-minute interval of time. Now, if we're focusing back on this chart, on the horizontal axis, we have time. So we have the month of March shown here and the month of April after that. This blue series, this is a pretty typical demand profile for a manufacturing customer. What we see here is they've got 5 different daily spikes. That's their production period during weekdays. They come down a little bit on weeknights when they're turning some equipment off. What's really cool here is this customer is great at turning equipment off on weekends. You can see how much their demand reduces on weekends. That's what we want to see for sure. Now, in the case of March, this customer's peak demand over a 15-minute window was about 1,215 kW. So those 3 rows that we looked at on the electric bill on the prior slides, they would have their demand charges based on this value. Now, let's say fast forward to the month of April, and something happens, and there's an hour of the day where we've got to have every single air compressor run. They've got the chiller system maxed out. Some weird was going on, and their peak demand jumps all the way up to about 1,500 kW. Well, that's going to show up on their electric bill, right? That peak demand portion of their bill is now going to become greater. And what's really important to keep in mind here is we want to make sure you understand how your specific utility is charging you for these peak demand events. There are some cases where your electric utility might not only look at your peak demand for the given month, but it might actually look back over an entire year, and you might have a portion of your charge tied to that highest event over the entire prior year. So if that's the case for this customer, if this day in April where they had everything on, if it really was that atypical, there's a chance they could end up paying for that for the entire year to come. So it is important just to keep in mind how you get billed for the power you use and how that might show up on your demand charges.
And I've got another example for this one.
Please do.
One of the customers that I work with, they used to start 4 electric furnaces on Friday afternoon, virtually at the same time. They had an operator come in and flip the furnaces on in that same 15-minute increment. And they were able to stagger their start times for those furnaces, and this brought their demand charge down by a whole lot over the course of the year. They saved thousands.
That is a great example because those furnaces, when they're warming up, they're going to take longer than 15 minutes, right? So if you kick them all on, then that 15-minute window, you have every single furnace trying to warm up at the same time. If you stagger those, you're absolutely right. You'll bring that demand charge down a lot. That's a great example. Thanks for sharing, Angelica. All right, now let's move on and kind of zoom way in, go from the facility level down to the equipment level. So what we're looking at here on the vertical axis, we have motor current measured in amps from 0 to 900. On the horizontal axis, we have time, but I do want to focus in on just how short this time scale is. We're looking at a 4-second window across the entire span. Now, what we've got here, the yellow line represents the amp profile for a motor getting turned on. So it starts at 0, about 1 second into this graphic, it gets turned on. This is an across the line sort of motor. So once those contactors hit, the motor starts to crank over. There's this huge inrush of current. It spikes all the way up to 900 amps, but you'll notice it really quickly decays down to its normal running amps. That stretch of time, it's only about 3 seconds. So we call this phenomenon motor inrush current. And we often hear from industrial customers of ours that, we don't want to turn that motor off because we're going to have to turn it back on and we're going to have to pay this massive penalty when the amp spikes. And they're not wrong. There is going to be a big amp spike, But again, the duration is really important to keep in mind here. So if we look at this, it's already down running at its normal amps within 3 seconds. It's probably more like 1.5 seconds, 2 seconds before it comes down to more of that typical level. When we think about how much of an impact this has on a facility's peak demand, which is averaged over 15 minutes, it's minuscule. So in this case, it might increase a peak demand value by about 0.3 kW, which is really small given that for most customers we work with, your peak demand values are going to be in the hundreds or thousands. So it's just a blip in the radar. That example Angelica gave before about the furnaces is a great counterpoint, because that's one of those ones where the increase in motor, or in that case, heater current and heater power, is a much longer duration, right? During that warm-up cycle, those might be heating up for 15, 30 minutes. But in the case of a motor just starting, it's this very short little window. So we've got a bit of an axiom we like to say when it comes to motors, which is it's almost always best to let a motor rest. And all we mean by that is the amount of cost you're going to save by reducing the energy use when that motor is not needed is almost always going to outweigh the penalty you pay for the super short time frame where you have that motor inrush current. So we want to kind of work with our customers to find opportunities to get equipment turned off when it's not needed. Okay, let's take this one step further here, and let's go ahead, let's stay on the equipment level, but let's figure out how to estimate input power for an electric motor. So let's say we walk up to a piece of equipment and we want to understand, hey, what is the input power for this motor? Well, we can pretty readily estimate it based on information that's already available to us. So the first thing we would go to is we would go to the nameplate for the electric motor. We would look up the motor nameplate. Maybe that's a 10 horsepower motor. Stamped right there on the nameplate. Great, we need that. That's our rated power. We also need to think about, though, is how hard is that motor working? And we call it our load factor. And the example I like to use here is a conveyor belt. So a conveyor belt, when it is fully loaded up with product, let's say it's fully loaded up with product, it's probably going to require that full 10 horsepower from an electric motor to keep the conveyor belt moving. However, when there's no product on the conveyor belt and it's just idling, it's probably only going to require 5 horsepower. We would call it a 50% load factor. To keep that conveyor spinning, it's just not going to require the full output of that electric motor. And we need to take that into account when we're estimating energy use for an electric motor. The other thing you need to keep in mind is the motor efficiency. You can also find this right there on the nameplate. It's usually going to vary from between 92, maybe 95%. And again, that'll get used in this calculation to estimate electric input power. So we can put that all together and say that the electric input power in kW can be calculated as a rated power measured in horsepower, times that load factor, times a conversion factor of 0.746 kW per horsepower, and divide that by the motor efficiency. And that'll let us estimate the input power for an electric motor. What I should say is this is just one way of doing it. So another way you can estimate the input power to an electric motor is to actually collect some additional data, right? If you have an electrician on site and they can tell you what the typical running amps is for that motor, and you know what the voltage is, you can use that to calculate input power a little bit different way, usually a little bit more accurately as well. All right, let's take this one step further too, because we've talked about input power in kilowatts, but oftentimes we want to know energy use in kilowatt hours or even energy costs in dollars. So once we have the input power for that piece of equipment, step one, and we want to calculate energy use maybe in kilowatt hours, we're going to take that input power and multiply it by the operating hours. Now, previously I mentioned how energy use is a quantity. Because it's a quantity, we have to think about it over some period of time. And so if we want to know, hey, what's the energy use for that 10 horsepower conveyor motor for a given day? Well, we need to know the average input power for the conveyor motor, which we calculated on the last slide. And then we have to think about what are the operating hours for a typical day? Maybe this conveyor motor runs 2 shifts, 16 hours a day. We can plug that in for operating hours to calculate the energy use for a day. If we want to know the energy use for a year, again, we'll take that average operating power, multiply it now by the operating hours for an entire year. So we kind of scale this to whatever period of time we want to look at. Now, if we want to take that to kind of the final step and calculate energy costs, we're just going to take our energy use measured in kilowatt hours and multiply it by our electric rate in dollars per kilowatt hour. You can kind of get a rough sense of this by just looking at your bill and looking at the amount you pay relative to the amount you use. Or you can check in with your Energy Trust representative and they can give you a little bit more dialed in estimate based on the rate schedule you're on. Okay, with that, I'd like to switch gears to electric and switch over to natural gas. And we're going to get started right where we did with the electric one on a natural gas bill here. So once again, you're going to have the very familiar information of the amount due and the due date in the upper right-hand corner. There's a lot more going on beyond that. So the first thing I want to point out is you'll see these units of therms, right? There's no kW or kWh anywhere on this bill. To keep things super confusing, we like to use different units for natural gas. So we use therms here. What's especially unusual, though, is your natural gas meter. It doesn't actually measure therms directly. It measures the volume of natural gas delivered to you, and it uses a billing factor to convert the volume of natural gas to the energy content of natural gas, which is in therms. And then you get billed based on that therms of use. To make the natural gas side a little bit simpler, again, there's not all these like demand versus energy charges. You really just have to pay for the amount of energy content of gas you use measured in therms. So if we look down below, we'll see all these line items and they have a rate associated with them. Each one of those scales to the amount of natural gas that you use. And so anything we can do to reduce your natural gas use is going to result in savings on your bill. And in this case, it really is the vast majority. So if we look at this $6,000 natural gas bill, yes, there is a $675 flat service fee, but then the bulk of the bill is tied directly to the amount of natural gas that you use. And again, that's what we can help support with some energy efficiency projects. Okay, so let's dig a little bit more into some of these units of measure. We talked a little bit about how the natural gas meter measures gas volume. Now you might see that show up in your natural gas bill in cubic feet, which is CF, or 100 cubic feet, which is CCF, or even 1,000 cubic feet, which is MCF. However, you don't get billed based on volume of natural gas delivered. You get billed based on energy content. That usually is represented in therms, right? Now, one therm is equal to 100,000 BTUs. You may also see it on your bill as an MMBTU. Some natural gas utilities bill based on MMBTUs, which is equal to 1,000,000 BTUs. Just a little kind of side note here, a BTU stands for a British thermal unit, and that is the 1 BTU is the heat required to raise 1 pound of water 1 degree Fahrenheit. All right, so let's do that same exercise as we did with the electric side, and let's look at a piece of natural gas-fired equipment to understand how to estimate its rated input. So in this case, if I were to walk up to a natural gas piece of equipment, I would find a nameplate. On that nameplate, I would see the input, and that is the amount of gas energy that's coming into the piece of equipment from the natural gas service. You're usually going to see that in units of BTUs per hour. Maybe it's MBH. You also could see a horsepower there. You might even say BHP, which stands for boiler horsepower. Now doing some unit conversions here, an MBH is equal to 1,000 BTUs per hour. A horsepower is equal to 33,465 BTUs per hour. It's also equal to 34.5 pounds of steam per hour. I talked about how the horsepower is often for boiler horsepower. We usually see that on large steam boiler systems, and so we can also equate that to just the mass flow rate of water going through that boiler. And that's where this 34.5 pounds of steam per hour comes from. Now, anytime I'm thinking about the input power to a piece of gas-fired equipment, we also do need to think about that load factor. And the example I like to use here is a very relatable one. It's my gas furnace at home, right? So my gas furnace at home has a rated input of 60,000 BTUs per hour. That's the same thing as 60 MBH. So you might see it represented either way on your gas furnace. However, today is a pretty mild day. My gas furnace is probably not cranking away at 60,000 BTUs per hour, right? That's how that piece of equipment is going to operate when it is fully maxed out. On the coldest day of the winter, when that gas valve is fully open and it's just absolutely cranking away, In reality, my gas furnace has a modulating burner. So on a mild day today, maybe it's only running at 30,000 BTUs per hour. Again, a 50% load factor. Okay, let's start putting this stuff together just like we did on the electric side. So if we can go ahead, we'll stick with my gas furnace example here. So if we can go up to a piece of gas furnace equipment and we can say, what's the rated input for it? How much natural gas is coming into that piece of equipment when it is operating at its design capacity? The case of my gas furnace, it's 60,000 BTUs per hour. We want to think about a load factor. And again, when I think through a load factor, I'm thinking about what's the load factor over the period of time of interest. So let's just, for this example, let's say I want to estimate my gas use for my house for the heating season. And I turn on my gas furnace October 1st. I turn it off May 1st. Over that period of time, my furnace is definitely not cranking away at 60,000 BTUs per hour, right? In reality, maybe it's averaging like 30% fire rate. There's some warm days it might not even turn on at all. There's other really cold days where it's running pretty hard. It would be pretty fair to estimate about a 30% load factor on that over the course of a heating season. And then the hours of operation, again, I said I'm turning that thing on October 1st. I'm turning it off May 1st. We could pretty easily calculate the hours between those two dates. We can put that all together and say the energy use for my gas furnace is the rated input in BTUs per hour times my load factor over whatever period of time I'm interested in, times my operating hours over that same period of time, and then divide by this conversion factor of 10 to the 5 therms per BTU per hour. And it's not shown on here, but the last step we could take if we wanted to is to convert that energy use into energy costs. And again, we could go to our natural gas bill and figure out our nominal kind of dollars per therm, or you could check in with your Energy Trust representative and see what's a reasonable assumption for your facility for dollars per therm. Okay, so now that we've reviewed how to estimate energy use for electric and natural gas equipment, we talked a bit about how to understand your electric and your natural gas bills. Let's talk about one place where you may need to apply some of these new skills. So the state of Oregon passed a building performance standard in 2023, and the building performance standard uses a building energy use intensity, or EUI, as a means to measure how well a building is performing relative to a benchmark, which they call an EUI target. Many buildings throughout the state of Oregon will need to demonstrate compliance with their EUI target by the required compliance date, which ranges from June 1st of 2028 through June 1st of 2030. I should also add that an EUI is just the energy use per square foot for a building, taking into account both electricity and natural gas use. So the image here shows how different building sizes are impacted by the building performance standard legislation. So on the left, we have non-residential structures, hotels, motels, that's it. So this is going to cover the vast majority of kind of commercial buildings. Notice that there are different tiers. We have tier 1, tier 2, and then the not covered tier. And there's different compliance dates over here on the right based on the building size. On the right, we have residential multifamily, hospitals, schools, dormitories, and university buildings, all shown kind of in this image. And again, we have tier 2 versus not covered, and they have the compliance dates based on building size shown here over on the right. One important thing to keep in mind with the building performance standard legislation is that there are exceptions for buildings where more than 50% of the space is used for manufacturing or industrial activity. Additionally, buildings used for agricultural purposes may be exempt. So the Oregon Department of Energy is administering the building performance standard program. So we encourage you to check in with them if you have any questions relating to if your facility is eligible for an exemption or what an appropriate EUI target is for your facility. That being said, we at Energy Trust can also play a role in supporting you as this building performance standard legislation is rolled out. We can help by supporting you with calculations to understand your current EUI and help reduce your energy use through incentives for energy projects and technical assistance. And with that, I'm going to conclude the presentation. Thanks so much for listening in and hope this helped provide more insight in understanding your energy bills and how to estimate energy use for pieces of equipment around your facility. Thanks much.